So from the generalized heat conduction in the Cartesian coordinate, we have the equation. We have derived this in previous video. That is the Biot Fourier equation. Okay. Also in the we can rewrite in this way: del square t plus q double dot by k 1 by alpha dot t by dot t. No, we have some simplified case for the plane slab. Okay, by adding some assumptions in the generalized heat conduction equation, we can get some temperature profile and the temperature distribution in the plane slab. Let us see. Let us assume that we are driving the temperature profile for 1D x direction steady state heat conduction. There is no heat generation involved, and the medium is having constant properties, that is k alpha or constant. Okay, since temperature is changing in x direction only, so temperature gradient in y and z direction are zero. For the steady state, dou t by dt is zero, steady state heat conduction equation. So we can see that the temperature is varying only in x direction, and we can write as partial derivative is equal to total derivative. So also we can write as dou square t by dou y square is equal to dou square t by dou y square. So applying all these assumptions in this Biot Fourier equation, we will have only one term as dou square t by dou x square is equal to 0, because all these other terms will become 0. On integrating, we will get dt by dx is equal to c1. Again integration karenge, we will get dt is equal to dx c1. Okay, so we can rewrite this as integration dt is equal to c1 integration dx. So dt का t हो गया c1 x plus c2 constant of integration. These two constant of integration we can find out by applying the boundary conditions. What are the two boundary conditions that we can use here? The first one is at x is equal to 0, temperature is T1. So at x is equal to 0, temperature is T1. We get T is equal to T1 0 plus C2. We get C2 is equal to T1. Second boundary condition at x is equal to L, the temperature is T2. X is equal to L, temperature is T2. From this we will get C1 and C2. As we get C1 and C2, we will put C1 and C2 in this equation to get the temperature profile. So by putting the C1 and C2 in the above equation A, we get temperature profile as linear profile. Okay. So we get as T2 minus T1 by L into X plus T1, or by rearranging the terms, we can get this as T minus T1 by T2 minus T1 is equal to X upon L. This is a linear temperature profile. Temperature is varying linearly from T1 to T2. So linear means a straight line. So at T1 and T2, the line joining T1 and T2 is a straight line. Since this is a straight line, it must so the equation of the line from the coordinate geometry, we have the equation of the line as y minus y1, y2 minus y1, x minus x1 upon x2 minus x1. Since the temperature is in y direction and length is in x direction, so substituting the terms in place of y and y1, x and x1, x2 and x1, so we will get the same result. This is pretty easy. No discussion on the heat flow rate. From the Fourier's law, we have q dot x minus kx dot t by dou x q dot a minus ka dt by dx. One thing that I would like to highlight here, as we can write q dot is equal to minus ka dt by dx. This term on multiplying with q dot into dx minus ka dt, integrate this parameter with the limit 0 to L, dx having limit 0 to L, and temperature having limit T1 to T2, we will get as q dot is equal to minus ka T2 minus T1 by L. Okay, and this is one way, and the another way we have, first of all we will find the gradient or slope or dt by dx. For this we have the temperature relation as this one. So rearranging these terms, we will get T1 as this, differentiating with respect to x. So we will get T2 minus T1 by L. Put dt by dx value in this equation, we will get q is equal to minus ka T2 minus T1 by L. As there is one medium, so k is constant, area is constant, T1 and T2 are constant as they are isothermal surface. L is constant, so overall the term q is constant. Okay, we can rearrange the terms in the q as T1 minus T2. If we take negative sign common, it will become T1 minus T2. Okay, divided by L by Ka, and L by Ka represent the thermal conductivity, sorry, thermal conduction resistance. L by Ka represent thermal conduction resistance. R conduction we can write as L by Ka. Okay, q dot is equal to, so we can write q dot is equal to, this is what, this is temperature difference divided by thermal conduction resistance, or R conduction resistance we can write as delta T by Q. Okay, for the metals we know that metals generally have high K values. For example, silver, copper, these have very high thermal conductivity value, and R is inversely proportional to K, so R conduction will be low for the metals, and for the non-metals it will be high. No, as we have the thermal conduction resistance, so also we have the thermal convection resistance. For example, this is a plain slab, the surrounding temperature is T infinity 1. This is the wall temperature TW1 of the slab of the left face. From the convection equation, q dot is equal to h bar a T delta T. Okay, we can rewrite these as 1 by h bar a. So 1 by h bar a represent our convection resistance. There is a very sharp analogy between the electric resistance and the thermal conduction resistance. So this is a wire of resistance R in which current I is flowing. The potential difference between the terminals is delta V. For the current to flow, there is a potential difference. So I is equal to delta V by R, or R is equal to delta V by I. Here, the I, that is the current which flows, so heat also flows. The potential difference is the driving potential for the current, so temperature difference is the driving potential for the heat. R is the thermal conductivity, so RTH is the thermal conduction resistance. R conduction we can write as delta T by Q. Simple. We will use this for the plane slab, either in the series or in the parallel connection. Okay, or maybe the combination of the series and parallel connection, as well as if the slab having the different sets of condition, like one side the heat is getting transferred through convection, conduction, convection, or whatever be the combination, we will see. So let us see. In this slab we have the surrounding, let's say there is some furnace or something like that. In between them there is a wall, of K is equal to constant having thickness L. The convection heat transfer coefficient is h bar I T infinity 1, and the temperature is varying in this way. T infinity 1 is greater than T1, T2, T infinity naught. So the thermal resistance diagram, since I is same in the series connection, so Q will be same everywhere. So our convection one, first thermal convection resistance, then conduction resistance, and again convection resistance. Q is equal to delta T. Delta T is this temperature minus this temperature divided by R equivalent. R equivalent is summation of all thermal conductivity. We can also write Q dot by breaking the whole circuit into individual circuit, like T from T infinity 1 to T1, from T1 to T2, from T2 to T infinity 2. Okay, we will get the same result. Whatever the question be framed, we can use it accordingly. Okay, so in this case we have the heat transfer by convection on both sides of the wall. There are some cases in which one side is having heat generation, then conduction and convection. So we can have this, for example, this is some heating element that is generating heat, so the temperature is T1, and at the other end temperature is T2, and as it T2 is greater than the surrounding temperature, so heat will be transferred from the right slab wall to the surrounding. Okay, so this circuit diagram can be represented as T1. Resistance is R conduction only up to this wall, up to temperature T2. Okay, so we can write Q dot is equal to T1 minus T2 by L by Ka. L is the length of the slab. Okay, and this will be equal to T2 minus T infinity O by R convection. Okay, very simple. Now we have discussed the slab cases separately. There are some cases in which slab can be combined either in parallel or series connection. We will see one by one. First, series connection. So two slabs are joined together of length L1 and length L2. First slab is having K1 thermal conductivity and other one is K2. So as thermal conductivity is different, the temperature slope will be different and heat transfer will be different. Okay, Q1 is different from Q2. So this is temperature T1, Q1, or conduction 1, T1. Okay, T1 is the interface temperature of both the wall. We can write Q1 as this. Again drawing T1, R conduction 2, T2, Q dot 2. Okay, Q dot 2 we can write as T1 minus T2 by L2 by K2A. Very easy. So this is the equivalent resistance diagram or thermal resistance diagram. Because in the series connection I is same, so Q will be same. Okay, and the resistance get added as simple as that. R equivalent is equal to R conduction 1 plus R conduction 2. So this is R equivalent between the temperature T1 and T2. Now we have the parallel connection. So these two slabs are connected parallelly of length L1, L2. Length may be same, may be different. Heat is flowing as Q1, Q2. Okay, let us assume that length is same. In the parallel connection, we know that voltage is same, but current get added. So total heat get added up. So for the upper slab, we have the circuit as T1, T2. No, since voltage is same, so here temperature will be same for both the slab. T1 is for both the slab and T2, the other end temperature is same for both the slab. Very easy. We can write Q1 as T1 minus T2 by RC1, Q2 T1 minus T2 by RC2. From the circuit diagram, from the basics, we know that 1 by R equivalent, 1 by RC1 plus 1 by RC2. Okay, we can write as R equivalent in this manner. Now, we have discussed the plane walls in series. We have seen only the R equivalent. Okay, now if the plane slab having different thermal conductivity, so the slope will be different. We will see how the slope vary according to the K value. I mean, let us see. So this is the K1 I mean slab 1 having thermal conductivity K1 of length L1 through which the Q1 is heat getting transferred. Interface temperature is T1. We will arrive on this conclusion later that this slope is less and that slope is more. Okay, in the series connection we know that q is same. Let us assume that area is same. We can write q is equal to minus ka dt by dx. Since slope is negative for this, it will be a straight line only that connect the t1 t2, and since t1 is greater than ti, so the slope will be negative. Okay, dt by dx is negative, so this negative outside the mod term, outside the mod term. So q is equal to ka dt by dx. We can write q1 k1 a1 dt by dx1. q2 इस तरीके से लिख सकते हैं. Since q1 is equal to q2, अगर q1 q2 को हम लोग बराबर इक्वेट कर रहे हैं तो ये दोनों एरिया a1 a2 बराबर है, बट k1 dt by dx1 इज इक्वल टू k2 दिस टर्म. ये दोनों का प्रोडक्ट सेम है, बट यहाँ पर चूंकि dt by dx1 यानी इसका स्लोप कम है. ओके, तो ये वैल्यू k1 ज्यादा होगा, इसका स्लोप ज्यादा है तो k2 कम होगा. ओके, दिस मीन्स दैट अगर यहाँ पर टेम्परेचर ड्रॉप कम हो रहा है तो इसकी थर्मल कंडक्टिविटी ज्यादा होगी. ओके, मतलब ज्यादा चांस है कि ये मेटालिक प्लेट हो सकता है. यहाँ पर टेम्परेचर ड्रॉप ज्यादा है, इसका मतलब इसकी थर्मल कंडक्टिविटी कम होगी. ओके, तो स्लोप ज्यादा है यहाँ पे. सो k1 इज ग्रेटर देन k2. अब ऐसा हो सकता है इन जनरल, दिस वाज द जनरल केस. सो इन सम केस दैट we can have as L1 L2 same. So we have seen that dt by dx1 is less than dt by dx2. तो इस केस में k1 was greater than k2. We can write dt by dx क्या लिख सकते हैं, t1 minus ti by L1 is less than this. L1 L2 same, this term will get cancelled. So on rearranging the terms, इसको by transferring t1 on this side and t2 on this side, we will have the interface temperature as is greater than arithmetic mean of the temperature. If k1 is greater than k2 and if reverse happens, this means that k2 is greater than k1, so arithmetic temperature, I mean, will be greater than the interface temperature. So this was the basic discussion on the plane slab wall. I hope I was able to make you understand. So thanks. I'm ending this. Bye bye. See you in next video.